10.2, arithmetic sequences and series. An arithmetic sequence is a sequence where you can add or subtract to get to the next term. So yesterday we looked at all different kinds of sequences. We had one where we were adding odd numbers, we were subtracting, we were multiplying. So today we're still looking at these sequences and series. So remember, a sequence is going to be that list of numbers, and series is when we add them all up. But now we're looking at arithmetic. So arithmetic is when the difference between successive terms is a constant. And this is called the constant difference. And the letter we use for that is D. So basically this would be like your linear kind of thing, right? We have that constant slope, we have a constant difference. So in number one, we're going to determine the common difference and then find the next four terms. So from negative 53 to negative 36, I would subtract those two, figure out if it's going up or down. And it's actually going up, right? The numbers are becoming increasingly less negative. 53 minus 36 is 17. So we are adding 17 each time. So if I had to say words, I would say we're adding 17. And then I'm just going to keep that pattern going by continuing to add 17. And our common difference D is, you don't really have to write common difference. You could just write D equals 17. So that's number one. So next we're looking at how to find the nth term. So it's really great that we understand that common difference, but sometimes we want to have that explicit formula. So instead of just continuing to write out a sequence, I could predict what's going on in the future. So this is a formula we're going to use for that. So a sub n would be where n is the nth term, so whatever term we want to find. So you could use like 20th, you could find a sub 20, you could find the 20th term. You use our first term, that's a1. N would be that number of term you're trying to find, and then D is your common difference. And we are going to simplify that when we use it. So this is an explicit formula. So for 2, we're going to practice finding both an explicit and a recursive formula for this series. So my series, my A1, first of all, is 14. And then I want to find that common difference. So what is going on here? It looks like I'm subtracting 11. I'm subtracting 11 again. So my common difference is negative 11. First, I'm going to look at a recursive formula. Those are actually easier to write. I know they have more parts and it seems trickier, but they're actually easier. So for recursive, I'm always trying to think first what's going on in words. And what's going on in words is that we are subtracting 11 from the previous term. So my first term is a sub 1 equals 14. That's how we always start one of these out. And then I would say my a sub n, I'm always going to take my previous term. My previous term is the one before a sub n. So a sub n minus 1. N minus 1 would come right before n. And I am going to subtract 11. And because I already have a1, this formula is for a2 or a3 or a4. And so I have to say that n is greater than or equal to 2. So that's my recursive formula. Now I want to come up with my explicit. So for explicit, I have this formula I'm working with, or this rule, and I want to always write it out because I'm learning it, I'm memorizing it. So a sub n, I am really looking for a formula for a sub n. So my a1 is going to be 14. N, I don't know. That's going to be whatever number I choose to put in. And then D is negative 11. And then I do want to go through and simplify this. So 14 plus, let's distribute negative 11 and plus 11. And then I'm going to rewrite it with the n part first, negative 11n plus 25. I wouldn't have to write n first, but it makes it look more like that y equals mx plus b form, which is kind of nice. So we have recursive, we have explicit. So for 3, we're finding the 41st term, so we're predicting off into the future. So that means I'm going to have to write a formula again. So we're going down by 7 every time. I always check all of them just to make sure it's not a trick. A sub 1 is 11. So first is to write that formula for the nth term. So that means I'm going to have 11 plus n minus 1 times negative 7. And then I'm going to distribute and simplify this. And then once I find that, now I want to find the 41st term. So I'm going to find, 41st. So I'm going to use n equals 41. So negative 7 times 41 plus 18. And we'll grab a calculator here. That is negative 287 plus 18, or negative 269. So sometimes in this next one, we're missing information. We are given our 44th term, where our n equals 44, and we're given our common difference, but we don't have a1. So I do have a formula that relates n and a1 and d. So I'm going to write that down. And a1 is what we're looking for, so we want to fill something in for everything else. So I would use for a sub n, I would use 44th term, a sub 44. A1 is what we're looking for. N would be 44 minus 1 times 8. Well, 44 minus 1 would be 43 times 8. And then I know that a sub 44 is 229. So I'm going to make that substitution now. So I don't have to use and say like 44th term. I know what that 44th term is actually equal to, and it's equal to 229. So now I'm just solving an equation. And I lost that. Where in the world did that go? Okay, here it is. So 43 times 8, I want to multiply that. That's going to be, let's see, 344. And then I want to subtract that on both sides. And so negative 115 is a sub 1. And that's all it asks for. I could go back, I could write a rule for this, but I have my a sub 1, I'm done. I've answered the question. So arithmetic means. So arithmetic means, what we're getting at there's 5 means between 6.2 and 1.6. So arithmetic sequence would be having that common difference. And so I need to figure out a common difference, 1, 2, 3, 4, 5, so that this could be an arithmetic sequence, and that common difference would be all the way the same, and there'd be 5 numbers in between. So it's kind of one of those things that's maybe easier to explain than to write a real definition for. So I want there to be 7 terms total. I want there to be an arithmetic sequence. So I want there to be 7 terms total. It's going to be arithmetic. I know my first term is 6.2, and my last term is going to be negative 1.6, and I'm just going to have to pause this for now. So our first term is 6.2, last term, A7 is negative 1.6. So really what we need to go from one term to the next and fill in all those blanks is our common difference. And we have not had to solve for that yet. So we're going to start out with that same formula for the nth term, or that rule for the nth term that we keep using. And let's see, we know A7, we know our first term, our n is 7, and d is what we're looking for. And then just like before, my 7th term, I can actually substitute because my 7th term is negative 1.6. And then 7 minus 1 would be 6d. And now I'm going to subtract on both sides and then divide. And so d, negative 1.3 is equal to d. So notice I left my d on the same side. I'm not like flipping sides there at the end or anything. It's all right to have our variable on the right. So that tells me to get from one term to the next, I need to subtract 1.3. So if I start with 6.2 and I subtract 1.3, now I'm down to 4.9, and then 3.6, and then 2.3, and then 1, and then negative 0.3, and then negative 1.6. So here's those 2 terms that I started with, and then I do have 1, 2, 3, 4, 5 in between, just like I wanted. So that's an arithmetic means. We're trying to come up with those other terms to make our pattern work. So next one, is we're going to just explore a little bit this idea of first differences and second differences. So if I have a sequence, just random, a random sequence, and it's like 5, 10, 15, 20, 25. My first differences would be that I'm adding 5 each time. And that's my first set of differences. First differences, because I just looked one time, the difference between each number. And if they are a constant, then it is arithmetic. And our other word for that would really be linear. So what about if I have a different random sequence? A different random sequence. And let's use like 1 and 4 and 9 and 16 and 25. These are perfect squares, aren't they? So if I'm looking at these perfect square numbers for my first set of differences, I have 3 and then 5. Let's start it with 0. So we can say 1, 3, 5, 7, 9. So my first set of differences are not a constant. But what if I look at my second differences? So that means take all the differences from the first set and look at what is going on between all of them. So if I look at my second differences, so my second differences now means I'm looking at between 1 and 3, well, I'm adding 2. Between 3 and 5, I'm adding 2. So if my second differences are a constant, then I have something that is quadratic, which should be pretty obvious because I was working with square numbers, right? 1 is a perfect square, 4 is a perfect square. So this is that idea of first and second differences. So when your second differences are linear, or your second differences are constant, that'd probably be better just to say constant, then we have a quadratic. So this brings us to our next example. We want to find a quadratic model. So a quadratic model for me is always going to be y equals ax squared plus bx plus c. In this chapter, I would trade out my y for an nth term. I would trade out my x for an n. But you could just continue to use this if you would rather. So there's no requirement that you suddenly use now a new formula for this. So whatever works. I really want us to recognize that these are the same. So they're not the same in that when I have a graph, right, I'm using all those in-between points. It's not just when x is 1, when x is 2, when x is 3. I mean, when we have a graph, we're really connecting that. We can look at like 0.3 when I'm looking at terms. So I do have just that list. There's nothing in between them. So they're saying quadratic model, but let's just double check that. My first set of differences is definitely not linear, but my second set is. So my second set of differences is a constant. Second differences is constant, so quadratic, and it does not have to be a 2, but the ones we've looked at so far are. So that means I know it's going to use that equation, y equals ax squared plus bx plus c. And I can think about how my first term, a sub 1 equals 0. So my first term is 0. That's going to be like a 1, 0. My second term is 5. That's going to be like a 2, 5. So I'm using everything as y and x. My third term is 12. So that could be like 3, 12. And I'm going to go ahead and substitute. And I'm going to use that y equals ax squared plus bx plus c. So again, you could use a sub n and you could use n, but I just find for most students this is easier. So that would mean my first one would be, let's see, 0, because remember these are x, y. So 0 equals a times 1 squared plus b times 1 plus c. So 0 equals a plus b plus c. We're just going through and simplifying them all. My second one would be 5 equals a times 2 squared plus b times 2 plus c. So 5 equals 4a plus 2b plus c. And the next one using 12 for y and 3 for x. So a times 3 squared plus b times 3 plus c. So we are going to have a system with 3 variables and 3 equations. So here's my system, right? All these simplified equations now. These are going to make a system. And in order to solve for a, b, and c, I do need to have 3 equations. So I have 0 equals a plus b plus c. I have 5 equals 4a plus 2b plus c. And I have 12 equals 9a plus 3a plus c. So this is my system. So it's evident I really want to cancel c out right away. They're all just like a 1c, so that's going to be pretty easy. I'm going to take my first one multiplied by a negative. So I have negative a, negative b, negative c, and add to the second one. And then my c's will cancel. Always make it so you're adding 0 and 5. Oh, 0 and 5 is a 5. This is a 3a and a plus 1b. So we're good there. Then I'm going to take the second 2, right? Because I've already used 0, I've already used 5. I've got to use 12. So, or maybe I'll just use the last one and the middle one. That would work too. So let's use, we'll do that. 12 equals 9a. There's so many different ways to go about solving. 3a plus c. And I'll make the first one negative again. Negative a, negative b, negative c. So 12 equals 8a plus 2b. All right, now I'm going to take these two and make a system. And I want to multiply the second one by a negative 2 so that I can cancel b's out. So 12 equals 8a plus 2b. And negative 10 is negative 6a minus 2b. I have to multiply everything by 2, the 5, the 3, and the b. And now when I add, I get 2 equals 2a. And so 1 is equal to a. So now I'm going to go back and use my 5 equals 3a plus b. And now I'm going to solve for b. So 5 equals 3 times 1 plus b. I could use any equation involving just a and b. I could use the one with the 12. I could use the one with the 3. I could use the one I multiplied. This is the easiest one, I think. So 5 equals 3 plus b, or 2 is equal to b. And then I want to find c. So for c, I'm going to use that 0 equals a plus b plus c. And I have so far that a is 1 and b is 2. So now I can solve. So 0 equals 3 plus c, or negative 3 is equal to c. So now I'm going to put all this together. This would be y equals 1 times x squared plus 2 times x minus 3. Or if I was going to write this with that other notation, I would have a sub n is n squared plus 2n minus 3. So it's kind of nice to solve it with y and x all the way through, but then we could just switch it to a sub n at the end if we want to. So last is arithmetic series. So remember, arithmetic series would be when we're adding up an arithmetic sequence. So indicated sum of the terms of an arithmetic sequence. And here are our 2 formulas. I really prefer formula 1. I know that we can also use formula 2. I just find formula 1 is the easiest for me, and it seems to be more useful. So I basically take my first term and my last term of all the things I'm adding, and then I multiply by how many of them there are divided by 2. So this doesn't have to, you don't actually have to have like an a sub 1. Like maybe you're adding from the 5th term to the 12th term. Then it would be like a sub 5 plus a sub 12. And then the end just is how many you're adding together. So I find that's my more useful one between the two of them. That being said, we do sometimes use formula 2. And there are students that are always, telling me, well, I use this one here. And that's fine. I don't care as long as you're getting the right answer and you're showing your work steps. I'm just telling you that personally, I find the first one to be more useful. So for 6a, I am trying to add up all the terms from negative 3 to 157. So this would be like my a sub n. This is my a sub n. So I'm just going to write down that formula really fast. n over 2 times a1 plus a sub n. So I know my first term, and I know my last term, but I don't know what n is, right? That's an issue. So I have my first term is -3, my last one's 157, but I don't know how many there are. And I don't want to keep going with the pattern and then solve and figure that out. So I've got to have a way to find n. So I'm going to go back to that rule or formula we have for the nth term, and we'll just plug in what we know and see if we can solve for n this time. So I do know that d is, let's see, up by 5 each time. It looks like plus 5 plus 5. So d is going to equal 5. And I know my a sub nth term is 157, right? I don't know what one it is, but I know it's 157. So I'll go ahead and plug that in here. A1 is -3, n is what I'm looking for, and d, of course, is positive 5. So let's go through and distribute. So 157 is going to equal 5n minus 8. So if I add 8 on both sides, 165. So n, let's see, 33 is going to be equal to n. Notice again, I left n on the right side all the way through. So now over here, now that I know my 33 is n, I'm just going to pop that in. And really then we're finding s sub 33, the sum of the first 33 terms. And this is going to be a whole number. I know that's a concern. It doesn't make sense that I would add up a bunch of integers and get a decimal. So don't let that 33 over 2 part scare you. This is 33 halves times. When I add those two, I get 154, which is even. So see, it's going to work. And then this is equal to, I really should be vertical, but I'm running out of space. It's equal to 2,541. All right, so on this next one, it starts at 10. 10 is my lower bound. And my sequence or series, because this is summation notation, we're adding them all up, is going to go to my upper bound, which is 32. So basically what this means is I'm taking a sub 10 and I'm adding a sub 11, I'm adding a sub 12, and I'm adding all the way up to a sub 32. So this one's weird. This is one of those ones where we're not starting with A1. So we're adding all of the numbers, all of the, I guess there'll be numbers after we simplify, but we're adding all of the terms from A sub 10 to A sub 32. So my S sub n, my formula looks like this. For the nth partial sum, I'm doing this. Only this time I'm going to make this, instead of A sub 1 plus A sub n, we're going to be doing A sub 10 plus a sub 32. So how many terms is that? So it might be really tempting to subtract them and say 32 minus 10, that's 22 terms, but it's not really. It's really 23 terms. And the reason it's 23 terms is if I think about, like, how about on a math assignment? I'm going to use a small number and then we'll go from there. What about if you were doing math homework and I said problems 2 through 5? Okay, so if I do 5 minus 2, I get 3. But this is more than 3 questions. This is problem 2, problem 3, problem 4, problem 5. The problem is when I subtract, I'm not really including this 2, right? I'm just looking at that difference. So it's whatever it is. If I'm doing 32 minus 10, I also have to add 1 because I'm including the 10 and I'm including the 32. It's all of them. So be really careful. So if I'm doing problems 2 through 5, it's not just 5 minus 2 equals 3 questions. It's 1, 2, 3, 4 questions. So I have to subtract and then I have to add 1. So that's why we're going to say that from 10 to 32 is actually 23 terms. So I need to find a sub 10 and I need to find a sub 32. So a sub 10 I find using this. It says n plus 6. So 10 plus 6, which is 16. For a sub 32, my 32second term, I need to do this also. So 32 plus 6 is 38. So let's see. So that means when I'm adding all of these, I'm just going to use S because 23 makes it look like the first 23, and we're not really doing the first 23. The one I'm starting with is 16. I'm ending with 38. So that's going to be, let's see, 16 plus 38 is 40, 54. So 27 times 23. So my sum is going to be 621. I guess I'll just write the S sub n there. So the sum of those 23 terms is 621. So this is the end of our 10-2 notes.